So last time we introduced two very important rules when we take the derivative, the product rule. And the quotient rule. The product rule is about the derivative of the product of two functions. So when we take the derivative, it's not the product of the derivative, but the summation. Okay, so warning not. Okay. So for something related to this, in the future you will learn this involution. So you will learn this in the future, like for example, the Fourier series. But for our derivative, we have this rule. And for the quotient rule, we start with a special case. Special case is 1 over G. The derivative of this is okay. Then you do this, we find the general case, the quotient. We view this as the product of F with 1 over G. So we apply the product rule, we get and so be careful. This for the product rule, what we have is the plus of the two parts. For the quotient rule, we have the difference of the two parts besides the denominator. Know the difference for the product rule and the quotient rule. Okay, then we verified two fundamental limits, very important limits. So for the first one, let's check with Sophia. How did we verify this limit? Do you remember that?
We drew some
Okay.
geometric shapes
Yes.
from sine 0 to sine of 5 or 2 or something.
Very nice.
Yeah.
So we give a geometric proof of this limit. Okay. Then after we verified this, we use this identity, a trig identity. So we use this algebraic proof. Okay, so we not only we know the limit, but we also know how we arrived this limit. Then another interpretation of these limits. The first interpretation, This can be viewed as the limit of the sine function. So the derivative, that is x. And when x is 0, the derivative at 0 is 1. And the second limit, cosine x, when we take a derivative. So this notation, it means we evaluate the derivative at this point. Similarly, we evaluate the derivative at 0, you get a 0. Okay. Then we use the formulas for the action, for the addition of angles. We get the general derivative. Again, not only the proof, but also how we get this. How we apply this angle, formula of angle addition. Key. Okay. Then we can take higher order derivatives. Second derivative. Okay, Zichen, how do you take this second derivative?
Take the derivative of the first derivative.
Yes. So the second derivative is the derivative of the first derivative. And we know what the first one is. Now it's just first derivative of cosine. By the second formula, we get this. Similarly, cosine x second derivative. Derivative of the first derivative. Negative sine derivative. That's by the first formula, negative cosine. Then some observation. The second derivative of both sine and cosine is the opposite of the initial function. Hey, hello. So both of them, they are on Zoom. You can see them on, on screen. Okay, I can.
It's okay, I can see. Oh, you can't see. It's okay, you can go ahead.
Okay, so they can see you now. Then I can change the output, you can hear them. Okay. Now have the second derivative. Let's see what's the third derivative. So for higher order derivatives, 3 or 4, even higher, we use this number, parentheses numbers. Okay, Sophia, how do you find the third derivative of sine?
You take the derivative of the second derivative, so it's going to be negative cosine x.
So it's derivative of the second derivative, negative cosine x. And Zichen, the third derivative of cosine x.
The derivative of the second is which is negative cosine x. So sine x.
Negative sine x. Sine x. Okay, one more step. So I will do it myself. Sine x. Derivative of the third derivative. And we have just done that. This is sine derivative of the 4. The second observation is that the fourth derivative of these two functions recover the initial function. Now we see if we go to the eighth derivative will be the fourth of the fourth. So fourth again will be the function itself. In particular, we have the formula sine x for n times sine x for all n. Similarly, cosine x, we take a derivative for n times cosine x for n. Okay, very useful formula. Now we move to the next one, sine, cosine, tangent.
That needs to be an integer, right?
Yes, very good observation. For all integers, 1, 2, 3, 1, 2, 3, because we haven't defined what's the half derivative. Okay, if we want to see what's the cosine x.
It's very hard to prove that, right?
Okay, another point. Let me finish this one. No idea. So again, so this is a guess, maybe an observation from the experience we observed this. Now you know how to, let me check. Sophia, how do you actually prove this? For all n. What method would you use? The method. We can put it for n equals 1, we can put it for n equals 2, maybe it's bit work n equals 3. How do we?
Induction.
Okay, yes, that's the keyword to prove this, mathematical induction. Okay. Next, we have the tangent. Derivative of tangent x. Okay, Zichen. So without any calculation, so what would you do to find the derivative of tangent?
Derivative of sine x over cosine x.
Okay, that's a very good approach because tangent is defined as the quotient. Very good approach. Sine x, cosine x. Okay, it's the quotient. We have the quotient rule. The quotient rule, let me copy. Maybe g squared. So at the beginning of this course, I would recommend you copy the actual formula, not just write it in your mind, but actually write it down. After you become more and more familiar with this, maybe you can skip this step. But in the beginning, copy the formula. Okay, so g is the cosine square, easy. F derivative, f is the sine, cosine. F sine, cosine derivative. Okay, we have what we need. We can continue. Sine. Okay, Sophia, what's the derivative of sine?
Cosine x.
Cosine x, cosine x. And Zichen, what's the derivative of cosine x?
Negative sine x.
Negative sine x. Now we manipulate cosine x, cosine square x. Minus is plus. Okay, Sophia, what's the numerator?
It is 1.
It's a 1 because the trig formula. Okay, this is good enough, but sometimes if we wanted something, not a fraction, we use this recorded definition. We have defined another trig function as 1 over cosine x. Okay, so using this new function, we can rewrite the derivative. So tangent x is secant square. Okay, very important formula. Okay, we mentioned this secant 1 over cosine. Let's find the derivative of secant. Secx. Okay, it's 1 over cosine x. Okay, so Zichen, how do you find this derivative?
It used the quotient rule thingy again.
Okay, it's a special case of the quotient rule. Again, I'm going to copy the formula. I'll copy the formula. In our case, G is cosine. Okay, so we have negative, they cancel each other. And the cosine, we want to avoid the fractions. We have some function we can use. Write this as x cosine square. We split this as cosine x. The first part is tangent x. Second part is secant x. Okay, so that's the first. Any question about these two derivatives, tangent and secant? Okay, if no, we will find the second derivative of tangent. I will give you a minute to think about this. How to find the second derivative of tangent? Sophia, what's the first step?
So you take the derivative of secant squared x?
Okay, so it will be the derivative of the first. The first is secant. The secant square, I write it as the product. Zichen, how do we go from here? How do we find the derivative of the product?
The other equation or formula.
The product rule.
One.
Okay, the product rule will be secant derivative, copy the second. Copy first, derivative second. And we have found it before, it's tangent. Okay, so this is one tangent secant square, another tangent secant square, so twice of this. Okay, the derivative of second of secant. Okay, Sophia, what's the first step?
Find the derivative of
Okay,
tan x secant x, which is the derivative of the first derivative.
okay, derivative of the first derivative. And Zicheng, what's next step?
The equation or the rule again.
What's the name of that?
The product rule.
Okay, yes. So next time see the product rule, make it more precise. So tangent secant square secant tangent. So secant. Okay, so the second derivative. Okay, so this is about the derivatives of these trig functions. In the future, we'll learn more about this. So for the moment, we'll move to the next section, a very important rule, the chain rule, very important. Make this. Very important rule. So previously, the product rule about the product of two functions. Vs, the product. So this is about the product. Use a short notation, FG. But the chain rule is about the composition. So we use this notation, compose T. Okay. So it's a difference of the objects for these two rules. The product rule we learned before is about the product of two functions, the derivative of this product function. And the chain rule is about the composition of two functions. So the composition, very simple example. So 2 sine x. So this is a composition of sine function with a cubic function. Sine. Sophia, what do you say about this function? What are the two components?
G of x is e of x, e to the power of x, and f of x is sine x.
Another one, e sine x. Zicheng, what about this one? Unmute yourself. What's G, what's F?
G is e to the wait, F is sine of x. Wait, I don't know.
So which one came first? So Gx is the interior function. Which one is the interior, e or sine?
Sine.
Hmm?
Sine.
So okay, so this time is sine x. And the exterior function is ex. Then the composition of f with g e to the sine x. The composition of sine with e sine x. Now you can see the difference of this. F composed g, sine composed e is different from e composed sine. Just finish this one. Gx. And we observe F composed G is different from G composed F. For the composition, we cannot change them, but for product, it's the same. Yes. Another difference of these two operations, composition and the product. Okay. Now we can the formula. If we take the derivative of the composition, so the formula is the derivative of exterior function at gx and the derivative of the interior function. Okay, so this time we have the product of derivatives, but at a different point. The interior function at x, the exterior function at gx. Okay, it's not. Okay. Let's give a quick proof of this formula. So to make the proof more transparent, we introduce an intermediate variable. So another increment. Then the derivative. The derivative is the quotient of the increment. The increment in x and increment in the value. So the value x to x plus h. If we take a limit, we get the definition of this derivative. Now we will do some manipulation. We will work under the assumption that this is not zero. We will see what happens if it is zero, but at the moment, let's assume it's not zero. This one quotient, I will split it into two quotients. I will copy the numerator to the first one, denominator the second one, and put something common in between. Okay. What I'm going to put is, I'm going to put this X H For the second part, if we take a limit when h goes to 0, we know the limit exists and will be the derivative. But for the second one, I will use the new notation we have introduced. U will be gx. This will be v, and this will be u plus v. Okay. So we assume that both of them are differentiable. They have derivatives. When h equal to 0, this converted to the derivative. When v equal to 0, this converts to the derivative. When we take a limit, then we can switch back to the this variable. We eliminate this intermediate variable. Okay, so this is our proof of this chain rule. The derivative of the composition is a product, but not the product. It's a product of this at gx, not at x. Very big difference. Okay, let's try some examples. Have something we have already over there. Let's try this one. The cubic power of sine x. Okay. So we want to find this derivative. Okay, let's Sophia, what's the first step? What do you guess I will do?
You
Yes, what would I do? Do you have a guess?
you would find the derivative of sine x.
Okay, that may be the second. The first step, I will copy the formula.
Oh.
All right. I'm going to copy this formula. I don't do anything in the first step. I just copy the formula. I want to make sure I get it correctly.
Because I get it.
Okay, yes, Sophia. So now what is f?
F is x cubed.
Now,
And
yeah. So it will be this derivative 3x squared. Let's make a little bit of extra space. Too crowded. So this will be 3 something square. So what is this thing over there?
sine.
Okay, how do you get that?
Sine x is g of x.
Okay, g x is sine, and we know the derivative is cosine. So there be cosine x. Okay, so then we can realize this 3. Okay, so that is the derivative. We apply the chain rule. the exterior function is cubic power, derivative 3 squared. 3x squared, interior function sine x. Interior derivative cosine. 3 sine squared cosine. Okay, we have another one. Sine a to the x. Let's find the derivative. Ah, terrible. You're right. Okay, Zichen, what would you guess my first step will be?
Write the equation formula.
Okay, the chain rule, the formula. Okay. It will be the formula.
It might be better to find out where the chain
Uh-huh.
in the formula,
You mean if I rewrite it using
where the chain.
this?
You have to change gx plus h minus gx. You change these two terms together.
Uh-huh.
Originally have fgx plus h minus fgx divided by h, right?
Uh-huh. You mean this chain? Uh-huh.
You change these two things together.
Uh-huh. Okay. So
Operation called bridge.
okay. So why it's called a chain rule? Maybe so Professor Drew commented. So this two is the chain connecting these two parts. Initially, that's the total derivative. So we put an intermediate term, the chain connecting them, to make this two quotients, two derivatives. But the chain gave us the total derivative. So why we call the chain rule? So that's one explanation for this. Hope to help you understand why it's called the chain rule. You can go through the proof, you can go through the formula. This is the important part. So very useful formula. Very useful formula. Okay, now Zichen, what is f for this function? What is g? Exterior and interior.
F is sine, the sine part, and then G is the e to the x.
Okay, what's the derivative of sine?
Cosine x.
Cosine. And what do we put over there?
Um,
Do we put x or should we put something else?
e to the x.
Yes, very good, very good. Because it's the derivative evaluated at gx. Gx in our case is to e to the x. So what we have over there is gx, not x. Very good. And Zichen, what's the derivative of gx?
Yeah, I don't remember.
Uh-huh. Okay, so we have learned that before. This derivative is itself. This is very special. So f derivative is cosine x. Okay, so the final result, cosine e to the x. It's the same. Let me not repeat. Okay, the third example, we change the order. Let's see what the derivative e to the sine x. Okay, let me give you a few minutes to try and enter your answer in the chat. Let's have 5 minutes break, and we'll be back at 47, and I will check with your answers for this question. Okay, 5 minutes break at 47. Okay, so Professor Drew, he had another comment about the point over here. So here we make the chain. We make the chain, one on numerator, one on denominator. So this cannot be 0 in this argument. What happens if v is 0? And in application, it's possible v is 0 sometime. Okay, Sophia, you want to say something? What happens when v is 0?
Then there's no derivative.
Well, it's not because when v is 0 for infinite many h, it means the values are kind of the same near x. In this case, the derivative of this is 0 at x. If this is 0, then we want to check this is also 0. So if this vanishes infinitely often, then we know this is 0, and we will check this also 0. So our objective changed. We change the knowledge of this is 0 will lead to that this being 0. Extra knowledge have extra information. Okay, so why it is when v is 0, then these two terms are the same. The numerator is 0. So this whole thing is 0. There's nothing to be considered further. So when this is 0, this is already 0. Okay. Maybe we should add a remark. So when v is 0, f g f(g(x) is 0. So because these two terms are the same. These are the same with the function at the same point, the values are the same. So this is 0. Okay. So the formula becomes okay. Okay. So a special case. Okay, Zichen, what is the answer to this question?
E to the power of sine x times cosine x.
Okay, very nice. Okay, again, I will follow the procedure, copy the formula, but this time f is e to the x, g is sine x. We take a derivative, it's the same. Derivative is cosine, so we get e to the sine x. Okay. Now we are going to return to something we have been promised for a long, long time. We promised we will find the derivative of this function. We promised this before. Now we are going to fulfill our promise. So before we move on to find the derivative, let's recall very important formula, the change of basis for exponential functions. For exponential functions, when b is not 0, 1, move this. of this. Okay, let's think about it for a second. How do you verify this formula? Sophia, what would you do if I want you to verify this formula?
So e to the power of x natural log of b is the same thing. It's the same thing as the composition of the functions e to the power of x and x log natural log of b.
So essentially, there's nothing to prove, but the only thing we are concerned is the appearance. It appears to be very different. So how to show they are actually the same? We can take the natural logarithm on both sides. We will take natural logarithm on both sides. Okay, Sophia, what's the natural logarithm of the left-hand side?
X natural log of b.
Okay, x natural log b. And Zichen, what's the logarithm of right-hand side? So when we take this logarithm of this power, the power goes to the front. That's our logarithm, root of logarithm. She is. Zichen, are you seeing something, Zichen?
Oh, I forgot to unmute.
Okay, let's try that again.
Wait, I don't remember how to do this. Wait, is it just e to the power of x times b? Like,
So
wait, I don't
the
remember.
formula, let me recall the formula. Logarithm x to the r. Do you remember this formula?
Yeah.
What's that?
R logarithm x.
Okay, very nice. Now let's apply this formula to here. What's the exponent?
X times log b.
Yes, so to the whole stuff. X logarithm b logarithm e. What's logarithm e?
What?
Oh, yes. Be more confident. This is 1.
Oh.
Okay, now you can see why they are the same. Because if we take a natural logarithm, they both give us this. Oops, you look at b. Yes. I copied wrong. Is that what you say? Okay, I copied wrong. Yes. That's why they are the same. Okay, so with this information, the derivative of 2 to the x, I want you to apply this chain of bases. What do you get? Okay, Sophia, what's the new exponent?
Now it's going to be e to the power of x,
Yes.
the natural log of 2.
Yes. Okay. Now you can see it's the composition of E with this. We will apply chain rule. Okay. Zichen, what's the first step I will do when I apply chain rule?
Write down the chain rule.
Okay, so you will do the same thing when you do the homework. Start with the formula, the chain rule. This time, f is exponential function, so it's the same. E to the x. Now the derivative x logarithm 2 derivative. Okay, so this time so this is a constant, a coefficient. So it's a linear function about x, degree 1. Okay, Sophia, what do we say about this derivative?
Let's 1 times natural log of 2 plus f times.
Just okay. For example, if you have a 2x, what's the derivative of 2x?
2.
Just 2. This is the same thing. They will replace this constant 2 by logarithm 2, the derivative, just logarithm 2.
Okay.
So logarithm 2, again, it's a real number. It's different from 2,
Oh.
but it's so
Yeah.
this is not a function, but just a number. Okay, so now we can switch it back. So 2 to the x is this. Now we can switch it back to 2 to the x. We can simplify our formula.
Wait, you don't have to use the product rule?
Okay, so very good question.
Wait. Oh, it's because it's just like it's it's just a number. Yeah.
Okay, yes.
Yeah.
Okay. Well, we could use the product rule. Look, let's go over the. So we could use, and we will get the same answer. Let's use the product rule. X logarithm 2. We will apply the product rule. Okay, the first one, Sophia knows. This is 1 logarithm 2. X, Sophia.
It's just 0.
Yes.
Oh.
And that's why we only need to have logarithm 2 because the derivative of a
It's a
constant.
Yeah.
Yes. So because in the beginning, you are not very familiar with logarithm. When you see it, you say maybe it's a function. But after you are getting familiar with this, it's just a constant.
Thank you.
All right. Now I want to give the result without any computation. I'm going to check with Zichen. What's the derivative of 3x? Think about this. Can you see some pattern from the first one?
3x, no, 3 to the x times log 3.
Yes, 3x log 3. And Sophia, 5 to the x. What's the derivative of this one, Sophia?
That is 5 to the power of x natural log of 5.
Yes. Okay. Now you see you can get this very easily without any difficulty. Okay, let's see what's next. I'm going with 2 to the sine x. Let's find the derivative. Okay, I will give you a few minutes to think about this. Enter your answer in the chat. Okay, so F1 is okay. Yes. Zichen, you can keep yourself unmuted. You don't have to switch back and forth.
I got the same thing.
Okay, okay. Okay, Zichen, you get the same thing. Okay, tell me how you get it.
First, write like the chain rule thing.
Okay, the chain rule. This time f is 2 to the x. So the chain rule give us, okay, the chain continue.
So then it's, wait. Then 2 to the derivative of 2 to the x is 2 to the x times log of 2. And then times sine x. Then derivative of sine x is cosine x.
Okay. Okay, that's one of the derivative. Let's try another formula we have premised. We haven't proved it yet. So x to the 8th power. We promised this will be a minus 1. To prove this, again, we will use the change of basis. So x to the 8th power, so proof. So here, x must be positive. That's our assumption. Okay, Sophia, I want to apply change of basis. What will the new exponent be?
It'll be
So previous is this. In the previous case, the exponential function x logarithm b. Now it's a power function, x to the power of a.
it's
So how do you get, yes? Yes.
natural log x.
Okay, Zichen. So Sophia gave you a formula. How do you verify this? How did we verify this one?
By like proving that both sides were equal.
Okay, so we take a natural logarithm of this, natural logarithm of this, we compare, they are the same. If we take a natural logarithm of this one, what do you get?
A log x.
What's natural logarithm of e to the a log x?
A log x times log e.
And what's log e?
1. Wait.
It's 1. Okay, that's why they are the same. Okay, so we have this. We want to find the derivative. Okay, Sophia, what would you do from here?
I would like
What would I do? Okay, what would I do?
you would write the formula.
I will write the formula. Okay, so f the exterior function exponential. Exponential function, so it will be just the function itself. And the interior, the exponent, we take a derivative of this. Okay, now we have something difficult. So I will switch back to the XA. A is a constant. Logarithm x. What's the derivative of this formula?
0. No, never mind. I never said
Okay. If it was a constant derivative, it is 0. But now we
Yeah.
have a x over here, it's a function. How do we find this function? Okay, it's something new we haven't covered, and we will cover it in the next section. But for the moment, let me give you something that we will prove later. Okay, so we'll prove this later if we use this knowledge. That's why we have xa minus 1. This minus 1 came from the derivative of a logarithm. Okay, let's try an example. Zichen, the derivative of x to the pi. What's this, Zichen?
The chain rule again. So
No. So okay, you now we have the formula. Let's just apply this formula.
So pi times x to the power of pi minus 1.
Yes. Now another one, x to the e. Sophia, what's the derivative of this one?
E x to the power of e minus 1.
Okay. All right. So we have something we haven't proved. And to prove this, we need another formula. Maybe that's not a formula, a method, but the implicit differentiation. That's very important. Okay, maybe a hint. So for that, it would be implicit. Okay, so implicit. Some of you may have seen this implicit function before.
No.
No, you haven't, Sophia.
No.
No. What about Zichen? Have you seen it before? Implicit functions.
No.
Okay, not really. Okay. So we want to know what is an implicit function. So to have a comparison, our known functions, they are explicit. So comparison.
Is it kind of like recursive?
What's that?
Is it similar to recursive formula?
The inverse formula, inverse function.
Never mind.
Okay, I'm not sure what that is, but you okay, you can make a decision later. Explicit functions. So to understand what is the implicit function, let's compare it with explicit function. That's the function we deal with every day. We deal with it so often, we often omit this term. We just say functions. Y equals x squared. Y equals ax. Y. Okay, so why are they called explicit functions? So here the dependence of this y on x is explicit. You give me an x, I do the computation, I find y. Give me x, I find y. Give me x, do the computation, I find y. The dependence is explicit. The implicit means the dependence of y on x. Y is still a function, but the dependence is implicit. For example, for this one, you give me an x. Let me check. So x is 1/2. How do you find y?
You plug 1/2 in x squared.
Okay. So
Or
here, y is square root y minus x squared. So here is a choice. Do we choose the positive square root or do we choose the negative square root? Y minus half square. So this also defines a function of y depending on x, but this dependence is not as explicit as we had over there. The dependence is implicit. This we call this an implicit function. More generally, an implicit function has the following form. Fitness. Some common notations for explicit function. The dependence is explicit, and implicit function give you an x. The value of y is determined by this equation. Okay. So this determines implicit. Even though this is an equation, but when x changes, y also changes. The dependence is implicit in this formula. Okay, so implicit in this formula, we can take a derivative of this equation. Let's see some examples. Okay, we'll start with this one. In this formula, x is the independent variable. And y, the dependent variable. We will take a derivative. When we take a derivative with respect to x, okay, Sophia, what's the derivative of x squared with respect to x?
2x.
2x. Zichen, what's the derivative of y squared with respect to x? So this time, y is a function of x. So it's the composition of this y function and the square function. So what rule do you apply for the composition?
Chain rule.
Yes, chain rule. So the exterior function is square to y and the y derivative minus 1, 0, 0. Okay, so this is our first implicit differentiation. Both are squares, but the derivative have different forms. X squared goes to 2x. Y squared, not just 2y, but with a term of the derivative, the implicit differentiation. Now you see the difference. Okay, so we can find this. So we solve the equation. Solve the equation. Y. That's the formula for this derivative. Okay, let's compare with the explicit derivative for comparison. We pick 1 minus x squared. Let's find the derivative. Okay, Sophia, how do you find this derivative? What rule do you apply?
You could apply
You have
the definition.
So here's we have this polynomial. Then we have the square root. So it's the composition.
Oh, chain rule.
Yes.
So it would be yeah.
So what's the derivative of f?
The derivative is 1/2 x to the power of -1/2.
What's the derivative of g?
That would be 2x negative 2x. Yeah,
Okay.
that's it.
Now we can write down the derivative. Get some space. We start from here. F, it will be 1/2 . And I will copy this interior function. And copy the derivative. Simplify. Let me make this look better. Simplify to be 1/2 and 2. Okay. Now we have two formulas for the derivative. First formula by the implicit differentiation. Second formula by the explicit computation. These two the same. Derivative, are they the same?
No.
No, looks different. It looks different. But if we plug in this formula into this, oh, Sophia, you saw it. They are the same. Yes, Sophia, you want to say something?
Nothing.
Okay. So if we plug this, that means a different color, into the formula, then we will get this. Okay. So this implicit differentiation, explicit differentiation, they give us the same derivative. So this function is obtained by solving this equation. It's one solution of the equation. That's why we expect it and we get the same derivative, even though they appear differently. Okay. Any question about this? We will have more about this implicit differentiation next time, and we will prove this formula, the derivative of a logarithm is 1/x. And Zichen, questions?